Now, our today's topic is refractions of light wave. And so when we are talking about refractions of light wave, it means change in speed and directions of light when it passes from one medium to another. And that is what always happens to we human beings also. When you are rolling on the ground, that is in air medium, and you are about to enter water, because water is denser than air, what will you do? You slow down. When you get out of the water, what will you do? You increase your speed again. So it happens to light wave as well. So let's say we have light wave moving from air medium to another medium denser than air. What will now happen? Let's say we have medium A and medium B. So if light wave is coming like this, on getting to the boundary of the two media, what will happen? The speed of light wave will change. Then how will we now show that the speed of light wave change through this ray diagram? It's very simple. What will just happen is, if this medium is denser than this one, it means the speed of light will increase. What will now happen? You increase the angle. This is angle of incident I. Then you now increase it like this. So since the angle of refraction is greater than angle of incident, it means this medium is less dense. Therefore, the speed here is greater than this. But what of if the ray of light move from less dense to dense medium? So what will now happen? That this medium A, this is B, and this one is less dense. That is, this one is denser than this. Just like when ray of light is moving from air medium to water medium. So in that case, it look like this. This is incident ray and this is angle of incident. Then on getting to this denser medium, the ray of light will slow down. In that case, the angle of refraction will be lesser than angle of incident. It will now look like this. Then do you know something? As you are increasing this angle of incident, the angle of refraction R also will be increasing. Therefore, the angle of incident very directly with angle of refraction. And again, the sine of angle of incident very directly with the sine of angle of refraction. We are going to apply that. Now, let's use this diagram to state the law of refraction. As we have two laws of reflection, we have two laws of what? Refraction as well. Now, very simple. Just use the diagram. You get it. One of the laws says the incident ray, this is incident ray, refracted ray, and this normal whole line on the same plane. That is, it's not that incident will be somewhere and refracted ray will be somewhere. Then the second law says the ratio of sine, that is sine I over sine R. The ratio of sine of angle of incident to the sine of angle of refraction is constant. Is equal to N. Is constant. And the constant is called refractive index of the medium. Then, do you now know how they got this one? Very simple. What they did is this. Like I told you that this one, the sine of this, very directly with sine of this. So that means sine I very directly with sine R. And normal thing, when you remove this one, you put equal to and constant. Therefore, sine I is equal to N sine R, where this N is our constant called refractive index. Therefore, make this one the subject of formula, mean N is equal to sine I over sine R. So from here, so that the ratio of sine of angle of incident to that of refraction is constant. Now, let's go to how ray of light moves in the glass medium. Now, look at it. This is a rectangular glass prism. It has rectangular shape. Then, it is made up of what? Glass. Now, let's use the diagram. When you have this, so the first thing you draw your what? Normal. You have Now, let's say you have your angle of incidence on the medium like this. But since this glass is denser than this, what do you think will happen to the ray? Will it move close to this normal, or it will move away from the normal? If the ray of light moves away from the normal, it means the speed here is greater than this. It means this medium is less dense. But now this medium is denser than this. The speed will reduce. Therefore, the ray of light will move close to the what? To the normal. Like this. So this one will now serve as our angle of refraction. Then, what will now happen to the ray? On getting to the what? On getting out of the glass, the speed will increase again. Then the angle, this one, do like this. So this is emergency. This is angle of emergency E. Now, don't forget to put your arrow. Now, that is how ray of light moves in a rectangular glass prism. Now, the next one is total internal reflection. Now, let me tell you about this total internal reflection. So what we mean is, that ray of light that passes through glass medium, it means it's part of it that passes through glass medium. We have part of it that reflected back. For instance, let's say you have these two media. This is glass medium, then this is air medium. Don't forget to draw your normal. We have normal like this. Then the ray of light is coming from the glass, is going out to the what? To the less dense medium, that is air medium. So we have this ray of light like this, striking this surface. Now, with what we have done before, what do you think will happen to this ray of light? Since it's coming from dense and it's going to less dense, will it move away from normal or move close to normal? But because the speed will increase, it will move away from the normal. It will now move like this. So that this angle will be greater than this one. So in this case now, this one will serve as our angle of incidence, while this one will serve as what? Angle of refraction. Then, do you know that not the total ray that strike this surface, that refracted back, some of them follow the law of reflection. So part of it will reflect back like this. The one that reflected back follow the law of reflection. The one that refract follow the law of refraction. So if you increase this angle of incidence, this angle of refraction also will increase. So if you have it like, you can show the second diagram. So let's increase it. We have this is our normal. So let's increase our angle of incidence from the glass. And the angle of incidence I. Then this one also will increase. So that will I point when the angle of refraction will be equal to 90 degrees. Then the point at which the angle of refraction equal to 90 degrees, when ray of light move from dense to less dense, is called critical angle. That is this incident ray. This one will not give this angle of incidence another name. We call it what? Critical angle. So if you are asked to define critical angle, it is angle of incidence in denser medium when the angle of refraction in the less dense medium equal to 90 degrees. Then don't forget, we have this one as our refracted ray. We still have our reflected ray too, but very weak. Like you have it here too, it's very weak. Then what do you think will happen if we should increase this one? You know, as you increase the angle of incidence, the angle of refraction also will increase. Now, to now look like this, so we have this one. So the moment we increase the angle of incidence more than critical angle, we have it like this. What will now happen? Our refracted ray will enter inside the glass. Are we now going to have two reflected rays inside the same medium? No, they will join hand together. So by the time this one comes and join this, we now call it what? total internal reflection. So this one and this, they will join together because this one will come inside now. They will now form total internal reflection. So if you are now asked to define total internal reflection, total internal reflection will occur when the angle of incidence in the world in dense medium is greater than critical angle for a ray of light moving from what? Dense to less dense medium, because we cannot have two refracted inside the glass. What are the two conditions under which we have total internal reflection? It's very simple. It's what you can easily get. The first thing is the angle of incidence will be greater than critical angle. If angle of incidence is not greater than critical angle, what will happen? We are going to have refracted ray and we are going to have reflected ray. It's not total again. It has split into two. But the moment the angle of incidence is greater than critical angle, the two will join together. We call it what? Total internal reflection. That's the first condition. Second condition is that the ray of light must move from dense to less dense medium. We have many applications of it, especially that what we normally have for mirage. It's an application of it. That when you are going on the road, you'll be seeing the pool of water on the road. Then, if you are not looking at image, you see the image of the tree beside the road through that particular pool of water you are seeing. Another one is wide field of view of fish. If you have a fish inside the pond, you see that before you will see them, you must have seen you. It's as a result of total internal reflection. We have it in periscope too. What of telescope? And also, that's what we use in optical fiber. There's another topic you will learn about optical fiber. It's an application of total internal reflection. So let's quickly derive the formula for refractive index under this same topic. So we have refractive index. Normally, refractive index is when layer of light move from less dense to dense. So in that case, we say sine I over sine R is equal to L. But this time around, the light is moving from dense to less dense. So we now reverse the case. Therefore, refractive index will now equal to sine R over sine I. So when this one equal to 90 degree, our sine of what? Refraction equal to 90 degree. What do we call this one? We call it critical angle. Therefore, refractive index is equal to sine 90 over sine C, because our sine I will be given another name called critical angle. So as in sine 90 is equal to 1. So another formula for finding refractive index is n is equal to 1. So because sine 90 is 1 over sine C, where C is a critical angle.